All right. Dimensionality reduction is actually a bit of mathematics that is really important, and this reflects a real problem. Imagine that you are, say, a Tesla. You're trying to drive down the road. You have a camera looking out the front, which is, I don't know what the resolution is, probably something like 4K by 4K, and probably like 30 frames a second. That's an unthinkable amount of data points coming in just a few seconds. You can't possibly process all that data. The same thing's true of a human. Your eyes are picking up that kind of data. Now, if you had to process all that data with your processors, which take milliseconds to do one computation, you'd get nowhere. And yet, if I throw a baseball at somebody's head, they immediately jerk back within like 50 milliseconds. Your eyes, your brain immediately figures out that this is important information, something is going to hit me, and you jerk back before you can even think. So that's attention. This is absolutely essential. The first thing you have to do is throw away almost all the data. You have to somehow figure out what part of the data is important and remove all the unimportant stuff in order to get anything done. And there's a famous psychological experiment where they have people playing basketball, and then they have a guy on a monkey suit ride a unicycle, a gorilla suit, right through them, and they tell people to count how many times the basketball is being traded. I did it, and you don't even see the guy in the gorilla suit. You can't believe it happened because you're watching the ball. You're focusing on that and ignoring everything else. This is the only way you can live. And you can see it mathematically. If you consider multi-dimensional situation, let me close these others. I'll just make a new one and see what it tells me. Close these others might be nice. All right, there we are. All right, so here, what I'm going to do is I'm going to have a line segment from 0 to 1. Then I'm going to make a square and a cube and a hypercube of various dimensions from 0 to 1. And I'm going to have 1,000 random points. And the question is, how many of those points are on the edge? And the edge means less than 0.01. So if I have a, okay. Should be coming. Yes, great. I got initialized. There we are. Now there we are. So if I'm in 2 dimensions, then only 25 points out of 1,000 are on the edge. If I have 2 dimensions, that's a square. Here's a cube. Only 29 of them are on the edge. But if I go up to like 1,000 dimensions, which is 1,000 input data points, which is really not much at all. Remember, your images are like 4K by 4K these days. Then every point is on the edge. So consider I'm trying to trace out the shape of some function. I can't just have a point on the edge and a point on the other edge. I need some points in the middle. Realistically, I need something like 10 points to trace out the curve. But how many points would that be? It would be 10 to the 1,000 points you'd need to trace out the shape of the 1,000 dimensions, and that's more than there are atoms in the whole universe. You could never handle that much data at all. So you can't possibly fit all the complexity of the input data at all. Remember, I said this is really stupid what we did. We took 784 pixels of like 28 by 28 and then turned them into 784 independent values and treated them all as equally important as we trained. I said, this is really stupid and really not going to scale. And you can see why. You'll never be able to trace out the full behavior of it. So what you want is to somehow reduce the dimensionality by removing the important stuff. And you can look at it another way. You can say, how far apart are the points in a hypercube of dimension 1? So it only goes from 0 to 1 in every axis. And the point is, once you get up to like 1,000 dimensions, the points are 12 apart. So they're so far apart, they clearly don't trace out the behavior of whatever you're measuring against these input parameters at all, and they never can. So what you have to do is find out which parameters are important and throw away the rest. And there is a standard way to do it called principal component analysis, which is very simple. So let's get some data to work with. This is going to be those MNIST images of handwritten numbers again. All right, and now we're going to find out how many dimensions we need. Now these have a total of 784 pixels in each image. So originally you have a 784 dimensional problem. And the question is, how many of those do you need? And the answer is, here, all you have to do is calculate the variance. What you do basically is turn the data set around in the high dimensional space until it gets skinny edgewise. You can see which parameters matter and which parameters don't. And that's what principal component analysis says. So if I want to catch 95% of the variance, I don't need 784 parameters. The amount that I need is in fact a lower number, 154. So there is, there is a hyperplane with 154 of the parameters that you can use, which will capture almost all the variance. And the dots pretty much fit on that plane. Only 5% of the variance goes off that plane. So it's really just a geometric fit. So you can use principal component analysis with a random forest and analyze them this way. And so it'll choose the best fit, it'll choose the best number of estimators and the number of dimensions. It'll optimize all that. So 154 dimensions would capture 95% of the variance. But if I optimize a random forest, then it will figure out, I'll just jump to the answer here, it'll figure out that you need 465 trees in the forest, but you only need 23 dimensions to achieve 85% success in categorizing the images. So this is dimensionality reduction. And now you can see what happened. You can reconstruct the images using only those 23 parameters, and this is what you have. This is the original image. This is the part of the data I actually used. And remember I said a human would just look at this and say, well, there's a vertical line, another vertical line, and a curve. They would reduce this to like 3 high-order constructs and work on that. And this is the machine learning model version of the same thing. It turned it into 23 significant things, and it's enough to do a pretty good job of classifying the images. So that's one issue. And another fun activity here is k-means clustering, which solves a different problem, but this is very old technique and very powerful, and again, very easy to understand. This is a way of classifying unsorted, unlabeled data. So I'm going to just, hey, I could just delete these. That might be a way to do this. How about, might be a way to delete them all. Anyway, I'm just going to go back and do them one by one. All right. So here, it's going to create a data set. And there is some way to delete this. Yeah, here. There we are. That might be the way to do it, so I'm having to log in again every time. All right, so I've got, that's not the right data set. All right, what's going on here? Should I run this? All right, I'm losing my mind. My attempt to avoid logging in again seems to be confusing me. All right, delete all that, put in that. There we go. All right, we want to sort these things. They're just Gaussian dots. So I have 2 dispersed, diffuse clusters over here and 3 tight clusters over here, and I want to sort this stuff into groups. So the way you do it is with k-means, which is an unbelievably simple algorithm and fast. It's been used for a long time. You do not need high powerful computers to do this. All right, let's put it here. All right. What k-means does is it guesses the centers, and I think this is it guesses centers, and then it just, once it chooses a guess for a center, it takes all the dots that are nearer to that center than anything else, and then finds the new average and moves there. So it's like a ball rolling down a trampoline, making a dent, making another dent. Now this is actually a good example. It made a bad fit. It combined these 2 into 1 and split this one into 2. So if I just run it again, it'll probably do better. I'm still getting it wrong. Let me see. Let me go back to my examples here. All right. That's actually pretty disturbing. I thought I even specified the random number, so you're supposed to get the same thing all the time. So there may be problems here. But anyway, this is what happens when it works. And so that's the algorithm, and you can see it go. Let's try this one. Here I specify the random seed for sure, so nothing should vary. You should get exactly the random numbers I got. Now let's try this one. Whoops, didn't put in the data. There it is, all right. There we are. All right, and what it's going to do is show you the steps in the algorithm here. Okay, so it starts out with random guesses. Now it labels the instances. So you have 2 centroids you've guessed here. So you take the ones that are closest to this centroid and call them yellow, the ones that are closest to this one and call them green. Now you move to the center of these dots. And see there's a bunch of dots to the left here, so you move that centroid to the left a little. And there you go again. And that's the problem as you move ahead. And here's the error measured going down. Now, evidently they've changed my libraries again. This one is not doing what it did before, so I'll have to find, apparently, I don't know what they've done. I'm getting bad fits where I used to get good fits. But bad starting, it used to be 5 gave me a bad starting value. Good results in 2 gave me another. Let me see what happens now. The seed determines the randomness. So if I change this to 2, looks like they've changed the processing in this library again in the last week or so. Now I'm still getting bad fits. I'm stubbornly getting bad fits all the time. I'm going to try one more and then I'm just going to move ahead and not worry about this. But I will have to fix this project apparently. Python people have hosed me again. Anyway, everybody in tech has ADD. They're always changing everything. Anyway, all right. Anyway, that's the game here. That's how it works. And another thing is, again, if you change the scale, it's like this thing is broken again. There's always technical problems. Now you change the scale, make it 10 times bigger in this dimension, and then you'll get this kind of fit because you told it vertical errors count 10 times more than horizontal errors. So it is not okay. It's not okay to have vertical misses. So you have to have horizontal stripes. That's the problem. Scaling really matters. Now you can make the moon-shaped data set. And this model only measures distance, so it's looking for round containers. So if you fit it, it's going to break them into many categories. Now, the textbook I got this from said this is a bad fit because it didn't sort them into 2 categories, but I regard this as quite useful because all I need is another layer where I tell it these 4 are category A and those 4 are category B. I can get the job done by adding another decision after this. But anyway, that's it. And so now you can do something awesome, which I'll just talk about. You can do semi-supervised learning. So suppose you have the digits data set here, and the first 50 images are here, and you have the first 50 labels. Now you have 1,700 images with labels. All right, if you give it the whole training set of 1,400 images, it gets 90.6% correct. But now I'm going to train it on just the first 50. And then, of course, it's much inferior, only 75% correct. So the question is, if I had to pay humans to label this data, and I don't want to pay them to label all the data, is there a way to save money and have less human labeling? And there is. Let me try and get rid of this. All right. What you do is first you instead of just taking the first 50 images that are random, first you use k-means and cluster them. Make 50 clusters. So you find the images that are similar. Then you take the images in the center of each cluster and look at them. These are the exemplars of the available variation of the images. Now you get humans to label them, only 50, and now you train on that. You propagate the label of all instances. So you decided that this is the example of a category, and all the ones in that group, once I label this as a 1, I label all the others 1, because they're close to this. Now, if you train on that, you get 85% accuracy, much better than 75%. But that's if you train on just the 50 you labeled. If you propagate the labels to all instances, you get up to 89%. And now, you remove outliers. You find the ones that are on the edges of the clusters and throw them away, because apparently it's unclear which cluster they belong in. You throw away 1% of the images that are furthest from the centers of the clusters, and now you get up to 90.9%, which is better than training on the original entire data set. So this is a very powerful technique, and kind of intuitive too. So that's what I wanted to show you there.